Going. So I have the pleasure today of introducing our seminar speaker, Dr. Ian Barnett. Ian is an assistant professor of biostatistics at UPenn, and he specializes in the development of statistical methods for analyzing high-dimensional data. His group has actually developed the methods and software behind numerous industry standard data processing pipelines. These pipelines are capable of modeling sparse and missing and multivariant intensive longitudinal data and translating these data into really clinically actionable measurements of behavior. He's also been involved in the robust statistical methods for mHealth. He's the founder of the Penn unit for mobile app sensing. And his career has really been dedicated to advancing digital phenotyping to understand disease complexities and enhance personalized patient care. And so today he's going to talk to us about measuring routine and behavioral variability through smartphone-based digital phenotyping. So I'll turn it over to you, Ian. Glad to have you here.
Yeah, thanks so much, Barbara. Let's share my screen. Really happy to be here. You guys really show out for these meetings. So we're okay. I full screen. You guys can see my slides.
Yes, looks good.
Okay, perfect. Yeah, so I'm going to cover a few topics today, but if you haven't heard of digital phenotyping, that's okay. I'll start from the very beginning here. My background is as a biostatistician, and so the first part of this talk is one where I will be talking about some of the literature in psychiatry to folks on the call who probably know this better than I do. So I'll try my best. But in terms of the structure, I'm going to talk about the importance of measuring behavior variability, and then I'm going to get into how smartphone data can perhaps be used to solve this problem of how do you get these kinds of frequent measures of a patient's behavior over time. So yeah, to establish the importance of doing that kind of longitudinal measurement, let's look at some examples. I'll focus maybe on the relationship right now between sleep and depression, anxiety as an example, but there are many cases where we really see the need to have more than just say like a baseline assessment of a person, and that we need to maybe measure them frequently over time. So variability, not just day to day, but even within a day, as we'll see, can in behaviors and in symptoms can be quite important and can vary pretty drastically. And so if you go and measure someone just at a single time point, there's a lot of noise associated with that single measurement. And there's really no solution except measure more frequently, which is perhaps easier said than done, but certainly easier when it comes to smartphone data, which is what I'm motivating here. So going back to the example I wanted to talk about of sleep. So, in a lot of studies, there might be at baseline something like the Pittsburgh Sleep Quality Index, the PSQI, might be administered, for example, at baseline, which is fairly comprehensive and does get a really good sense of overall sleep behavior for a particular person. But so I'm highlighting a couple of questions in the PSQI. Many of you have probably used this or seen this and are familiar with it. But for example, you might be asked, when have you usually gone to bed? How many hours of actual sleep do you get per night? During the past month, how would you rate your sleep quality overall? These are the kind of questions that are asked. So I just want to point out that these questions are kind of meant to capture average behavior and not variability, right? So you could have two people that have the same average sleep duration, but one person, if they sleep 7 hours every single night, what if there's someone else who sleeps 9 hours one night and 5 hours the next? Those are quite different in terms of behavior. Even though if you just reported the average, you would not be able to tell the two apart. And that variability in sleep has actually been well documented. It's being associated with trends in people with major depressive disorder. There's also been animal studies, but essentially like linking and finding in some cases, it's believed that there's like a bidirectional relationship between mood, depression, and sleep, as in, it can cause insomnia, and poor sleep can also lead to depression. So it's a kind of an intricate relationship, and there's a lot of studies both in humans and animals in controlled settings that have established this to varying degrees. But it really goes to show that even if we know someone's average behavior, if we want to know how they're maybe how depressed they are on a given day, it's probably most important to see how have you been sleeping lately. That's going to matter more than just knowing average behavior. So another example is that in this study, it was looked at sleep loss prior to the assessment date was seen to be associated with higher suicidal ideation in patients with a history of suicide attempts. It was noticed that if you had no history, there was like no effect. But over here, essentially, we're saying, did they have sleep loss? No, they didn't. Yes, they did prior to assessment. And you can see that amongst those with suicide attempts, there was an increase. This was seen to be statistically significant. So, you know, it can get quite complex, but there's probably something there in terms of, and maybe we're not completely nailed down on effect sizes, but there's a preponderance of evidence that kind of points to a relationship here where, you know, maybe just that single PSQI that you took at baseline might not be able to help you on a day-to-day basis, say for the purpose of doing an intervention, for example. So that's kind of the punchline here, and I teased where I was going with this, but if we're not happy with single assessments of sleep and we need to do a better job of capturing variability, what can we do instead? Now, I'm going to also give one more example, which so far I've been talking about maybe daily level measurements, right? Like if you're talking about sleep the day before and whatnot. Sometimes, in some cases, if we go away from sleep, it's also variability within a day, which can be pretty drastic and important. This is another study which looked at kind of measured people throughout the day and had them self-report on their mood and on their affect. And what you end up finding, I didn't label this y-axis, but higher on the y-axis is you know, a more positive affect, and you're in a worse mood here in the evenings, as you can see. So you can see that for the depressed subjects in this study, this is the average trend in the study. There's a pretty huge, like depending on the time of day of when you asked someone these questions, really dictated the response. If you ask them around noon, maybe they're up and at 'em, maybe they're in the middle of their routine, it's having an impact on their actual their mood at the time. And whereas if you're asking them at like 10 p.m. at night, it's a different story, and they're reporting something a bit different. So even if we have a measurement on a time of day, for some symptoms, for some and for some behaviors, it may matter what time of day we make that assessment. So we can see that maybe you look at this picture and you say, well, okay, you know, it would be great if we could look at someone's life 24/7, as long as we are like preserving privacy, of course, but that would give us the best window, but that's perhaps unreasonable. And so I'm going to talk about the potential for smartphone data to perhaps at least help in this regard. So so far I've talked about behavioral variability over the course of days and within a day, and how we've seen empirical evidence of that in a lot of cases for a lot of behaviors and a lot of symptoms. And I do like to talk also in a broader sense, this term, it's in the title of this talk, digital phenotyping. And so kind of taking a step back, one problem which plagues a lot of areas of research, but particularly in psychiatry, is phenotypic heterogeneity, right? Like the example I'm pointing out to here is, if you imagine over here, what if you have what if you want to do a case control study and you have people without depression, people with depression? How are they diagnosed with depression? Suppose that one of the instruments used in their diagnosis was like the PHQ-9, and it's not always so simple as this, but just for the purposes of illustration, imagine that you said, okay, if you scored a certain score higher on the PHQ-9, you know, what if you scored 6 or higher? I don't know, whatever the threshold is that was used for establishing the diagnosis of depression. Well, that's a combinatorics problem. How many ways can you be diagnosed with depression? There's many pathways to getting that label of depressed. So there might be people who are there because, they answered poorly on the sleep-related questions, or they've had suicidal ideation, but they need not have both. And the set of symptoms that are required for a diagnosis of depression are not always the same, and there's not always overlap. So that's what I mean by heterogeneity amongst these diagnoses. So this can cause huge problems. Like, for example, we look at family-based studies that showed maybe that did a good job in the 80s and 70s and 80s and 90s of using family-based studies to estimate heritability of some of these psychiatric disorders. Then when we go into the early aughts and we're doing GWAS and sequencing later, and we're finding out that, where is this missing heritability gone? This gap between what we expected to find and what we actually did find. Well, even if you have 10,000 people in a sample, if you're doing like a logistic regression and you're grouping all your cases together, if you're saying I have 5,000 people with depression and 5,000 controls, and you do like a logistic regression, you're saying all the cases, all the people with depression are ones and all the people who are controls are zeros. Well, if there's heterogeneity amongst those cases that you're not accounting for, this is going to muddle your signal. And it's widely seen that this is a big problem, and perhaps a reason why when some of those early genetic studies where you were not kind of find that gap emerged between what we expected to find in terms of heritability of some of these disorders and the amount of heritability explained by variants found. And so this problem, here's another problem, which is not just the importance of measuring things over time, but a lot of these phenotypes themselves were complex. And maybe it's not sufficient to treat. I'm going to stick with this depression example. Just say you have depression and throw you all in the same bin. We need to and take a broader view. Now, this is not a controversial statement I'm making here. I think I'm preaching to the choir probably to everyone on this call. But another thing that, one of the goals of digital phenotyping is essentially to help establish these kind of broader multivariate phenotypes rather than forcing everyone to have a single bin, like a personalized phenotype based on a broad spectrum of behavior. So let's get into the nuts and bolts. Smartphone data. The kinds of sensors you have on your smartphone. We have GPS, we have call and text logs, we have accelerometers. We have phone activity like screen on off. We also have a lot of apps for these digital phenotyping studies that collect the sensor data, also have built-in EMA, where on a schedule, self-report is sent to patient phones where they can respond to self-report. So we generally refer to these over here, these like sensors and phone metadata that are kind of collected in the background just through everyday use. We call this passive data because it does not require active involvement of the patient to give us this data. They just need to use their phone as usual. Now, during recruitment, they're told, of course, everything that is going to be collected and who's going to look at it and whatnot, and they have to give that permission. But once they've given that permission and they install the app on the phone, this is collected without requiring them over the course of follow-up to do anything more than what they normally would be doing with their phone. And so we call this kind of passive data and active data, where this is, of course, the self-report does require active involvement. So the reason we make this distinction is because ideally, especially in long-term studies, it's not super feasible to collect self-report, especially if you want to follow someone for a very long time. There's a huge body of research that has studied adherence and dropout in longitudinal studies. And even if you're heavily incentivizing people to complete their self-report, people just get tired of being in these studies. And if you're trying to follow someone for a year, they're going to drop out. There's been a lot of studies that show how long will people wear their wearable devices. That's even harder, right? But even when we're just asking with respect to self-report, there's adherence which decays over time. And so one thing that doesn't decay over long periods of time is passive data. So why do we care about this? It's because, well, for a lot of this, if you think about one of the holy grails in in psychiatry is, for example, suicide prevention. And for something like that, even people who are at high risk, you can't just have a 2 weeks, if you want to study suicide attempts, not even ideation, like what if you want to really study suicide attempts? You can't just follow people for 2 weeks with intensive deep phenotyping, because the rate of suicide, you could have 1,000 people in your sample and no one would attempt in 2 weeks, perhaps, right? Like it's rare even amongst people at high risk. You really need to follow people, a cohort, over a long period of time. And are you going to be asking them every day? We've already talked about, for example, mood fluctuations over the course of the day. Am I advocating that we would say, okay, have them give self-report of their mood 4 times a day for a year? It's just not feasible. If people did that, great, but it's not feasible. And this is not even discussing the fact that self-report has other biases that are associated with it, particularly when it comes to reporting on suicidal ideation. So there's a lot of attractive properties of saying, I realize that, of course, getting into a person's head is easiest to ask them via passive data. But what if their behaviors leave kind of a footprint of, looking at how mobile they are? What if there's someone who, before they attempt suicide, they stop going to work? What if they go on a social island? They are normally communicating with their friends and family, and that ends, and that's evident in their call and text logs for the days leading up to a suicide attempt. What if they start sleeping poorly? Could we estimate sleep all from passive data? Each one of these alone might not be sufficient, but if we see warning signs across many domains of behavior, this could perhaps be informative in the context of an intervention. So this picture is telling a big story, but a lot of my research is actually focusing on taking this data, which can have a lot of missingness in it, and also this raw data itself. Like if you think about GPS, what does this data actually look like? It's a latitude longitude coordinate pair, like where are you, accompanied with a timestamp. Now, if I were to give my clinical collaborators like a bunch of this GPS data, they wouldn't know what to do with it, and rightly so. What would be helpful is turning this into, say, a bunch of, say, daily features, like what if instead of giving them just the raw data, we can derive how many minutes did a person spend at home? How many significant locations in their life did they visit? What was their distance traveled? And these become more clinically actionable. These are variables that we could incorporate in, say, a predictive model, rather than the raw data alone. So there's kind of 2 phases to digital phenotyping, which is going from this raw data and turning it into this nice, pretty data frame down here, which is all colorful. Here, each column is representing a different day of follow-up. This is actual data from a patient with schizophrenia from a previous collaboration of mine. Each row is a different feature that's derived from this data. So, the green ones are, if you can't read this, that's fine. This is not an exhaustive list either. This is just a subset of the features that we derive. We look at, your call activity, text activity. The purple features here correspond to GPS-derived variables. I mentioned like time spent at home. Also, how much missing data there are. That can be a feature itself. Again, this is not an exhaustive list. We also have the sleep-related features that you're not seeing here, and activity-based features as well. You'll notice, though, that it's fairly dense when it comes to, like, we have GPS every day, and so we get, purple and some days there's no social activity, but essentially all the data is observed here. And if there's missing data, like in the case of the social data, it's a true zero. Like if there's no data on a given day, that's because there were no text observed. It's not because we're missing the text logs. We have complete data here. Notice down here, these survey IDs. For this study, this is the self-report. This is the active data. That's the orange. And here you can see that they were sent 3 prompts a week, and they weren't actually answering them on the same day. So this is kind of showing how irregular it can be. Like, I think this response right here was responded to 2 days late. And, obviously, this data is going to be, we cannot be asking them constantly to do self-report. So this is going to be more sparse. But this is kind of what the data looks like after we've gone through phase 1. Now, in my talk today, even though actually much of my work, I would say most of my research as a statistician is focused on taking this sparse and missing data here and producing this nice longitudinal data frame. That's not the point of my talk today. That gets into, I think there's most of the more interesting statistical questions go into how you handle that missing data, how you handle that sparse data. I'm not going to get into the details of that on my talk today, but that is more my passion. However, equally important is actually, and perhaps more exciting to the people on this call, is once you have this data frame, relating it back to clinical measures, making it clinically actionable. So, while both steps are equally necessary to get there, I'm going to be talking about maybe once we have this data frame, what more we can do with it. Okay, so this is just kind of zooming in. Actually, I already kind of summarized this, but let's move on to, oh, and I didn't number this right. There should be a 3 here, not 4, but let's move on to some more details on the examples of quantifying behavior. Like, what are those features that we get? I'm going to talk about some routine measures, some mobility measures. But hopefully at this point, everyone's with me that like that there's a potential for smartphones to perhaps fill this gap a little bit and provide, even though the data is messy and there's a lot of missingness to it, there is really important information there that we can use to derive behaviors over time, over a long period of time, just based off how someone is using their phone naturally. And so with that, let's look at some of the behaviors we quantify. So this is a recent work that we published in Biometrics recently, which took activity data, namely we took screen on off data and accelerometer, and we were trying to quantify a person's strength of routine based off of their phone use. Now, and a running theme throughout all this, and again, this is always going to be a limitation of smartphone-based digital phenotyping, is we are trying to learn about a person's behavior through how they use their phone. And that is not always a perfect proxy. It is often not, right? How my phone's behavior is not always going to be representative of my own. So in a lot of these approaches are trying to bridge that divide and say, let's acknowledge the problems that come with smartphone data and how it is not representing the person's behavior. It's going to be correlated and it's going to show a window to it. But it would be a mistake if we said that the smartphone's behavior was exactly the person's behavior. So in this case, we are using smartphone data to quantify a person's routine. But this quantification of routine is purely based off of phone use. If your phone is not a big part of your life, if you don't use it much, this measure isn't going to be as good for you. It's going to contain less signal. So this is always a disclaimer with this. Like, these features are useful, but whenever we talk about routine, if we say that we have a routine metric, we always have to qualify that this is based off of phone use. So that being said, and I won't dive into it, but we have like a missing data imputation procedure. What's really nice about this is that accelerometer data can often be missing. Basically, your phone has really good accelerometer on it. What does an accelerometer do? It measures the X, Y, and Z direction of basically acceleration of your phone. And it's often at like 10 hertz, meaning like 10 measurements a second of this, which is a lot of data. However, if your accelerometer is always on and always recording, a person's phone is going to burn out. Now, one thing that is super important, remember I stressed this for smartphones, is that we want to follow people. This is designed for longitudinal studies. We want to follow someone for long periods of time. It's really important that we collect this data without adversely affecting their battery, because what will happen? People will uninstall the app. If they come in and their battery lasts the full day and they install this app and suddenly their battery runs out the next day, maybe halfway through their day, they're going to say, I'm done with this. I'm out of this study. This is not worth it. And so we cannot just constantly be collecting accelerometer data, because it will drain the battery. Their phone will go hot and it'll affect its performance and they'll uninstall the app. So what do we have to do? Most apps that collect this kind of data have various like interval collection schemes. A common one is exactly that, planned intervals. So maybe they'll do 10 seconds of data collection for accelerometer, and then they disable it for 50 seconds, and then they enable it for 10 seconds, and then disable it for 50 seconds. So you almost have these planned gaps in their data. So a natural question is, can we do imputation on this? And so now beyond those planned gaps of missing data, there's also just missing data that's due to maybe they turn their phone off for several hours. This happens. And you have huge gaps in the data. What can we do then? How do we account for that then? What if you have 20 hours of great data and 4 hours of missing data? Do we throw out the entire day? That would seem like a waste. And we don't have to if we take advantage of the multimodal nature of the data. So this is what we've done here by, for example, if we look at screen activity, phone on, phone off, and accelerometer data, what's nice about screen activity is that it is never missing. If there is a long period of time with no screen activity, that's a what we call like a true zero. It's not missing. If there was no phone activity recorded, you were not interacting with the phone. That is just, that's the truth of it, and that is never missing. So if you have a data stream which is complete, such as screen activity, and then we have an accelerometer which has sporadic missingness, and they're correlated. If you're using your phone a lot, the accelerometer is picking up a lot of motion. This forms the basis for a great imputation. So anyway, we have an imputation procedure for the accelerometer data based off of the screen count data. It gets a little fancy because we account for time of day in our imputation. So we have like time of day random effect. But long story short, if you look on the right here, this is a person. Each bar here represents a 12-hour period. But you can see that like this is at night when they're not generally using your phone. And basically, we try to estimate this latent state of active versus inactive. Now, how do we turn this into a quantification of routine? I'll get to that in a second. But to tease it a little bit, in essence, if you look at these random effects, like these are tendencies for hour of day. So like what this is saying is that, actually, let's look at these 4 right here. This is a little after midnight. What we're saying is that the transition from an active state to an inactive state is really high right here. This is probably corresponding to when they're going to sleep. It's not going to be perfect, again, because the phone's behavior is not the behavior of the person, but this is probably preceding when they're going to bed. They're going to bed a little after midnight. And so we're getting a lot of transitions from active to inactive around then. If there's someone with very little routine, these are going to be fairly flat. So we came up with based on this model, we came up with a statistic which is quantifying strength of routine based off phone use. I mentioned that rest and active phone use do not equate to whether or not you're asleep or awake. So we have another approach, which is the semi-supervised approach, which, just to demonstrate this example, if you were to guess, each row here is just screen on-off data from one patient with schizophrenia. If you had to guess when they were sleeping, you could eyeball this, right? Your eye kind of trails down like, okay, they're going to sleep around midnight, a little before, a little after. And then they're waking up, 7, 8 hours later. And this seems pretty good. But if you just, what would you do about this day? This is perhaps a day where, are we going to claim that they slept for 13 hours? But I would say that probably, maybe they just didn't pick up their phone this morning. What you end up seeing is that if you just assume that the behavior of the phone is reflective of the behavior of the person, you end up way overestimating sleep. Because you're not always on your phone. You're not on your phone 24/7. If you're not using your phone in the morning, it would not be accurate for me to say that you were sleeping that whole time. That just means that this is representing a gap between phone use and personal use. So how do we overcome that? We can use some amount of self-report. So what we have done is we look at your history and we can make an educated guess if it's missing data or if it's true zeros. So that's essentially what we've done to say what is happening here. So this might be a patient where you look at a person's history. And of course, we do this in like a quantitative way. But you can, if you have an extensive history of a person, you can learn about their routine and patterns of behavior. You can make a more educated guess if they were in fact asleep here or if they just weren't using them. So that's what I was getting at there. I just want to jump ahead to using this in practice. This is from a different study of a patient with depression. Each row here, the black bar represents our sleep estimates. The red X's actually correspond to self-report of basically every week they answered the question of when did I go to bed on average the previous week, and when did I wake up on average the previous week. And that's what the red X is representing. And that's why you only see one every 7 days here for this person. And they just happen to actually say the same time for the consecutive weeks here. But they basically, this week they said they went to bed at midnight the previous week on average. And they said the same here. No, it's like 11:30 actually. And then they woke up at 8. That was their self-report. So we wanted to see, okay, if we just looked at how their phone was being used and plotted this, it's not doing too bad, but I would say it's still overestimating sleep probably, right? So we have nightly sleep estimates, and you can kind of pair it with what they said their average behavior over the previous week was. And it's roughly okay. And you might look at this and believe it. Now, with our approach, we do this kind of penalization, and we bring in some self-report to just overcorrect for this bias, which always leads to overestimation of sleep. And oops. So remember, this is what our estimation looks like if we don't have any self-report. But when we try to correct for that bias, this is what we get. And actually, this is probably more realistic in terms of sleep. We go from like an average of 9.5 hours of sleep here to around 8, which is exactly what they had told us. So you might say it wasn't so bad. Let's look at a more egregious case. Look at this. This is a person who does not use their phone much. Here, just using the phone alone, we're way overestimating sleep on a consistent basis. Are you telling me that this person slept for 17 hours this night? No, they just weren't using their phone that much that day. And their self-report is kind of confirming that. This person also is saying that they're sleeping about 8 hours a night. But their phone use is so sparse and so sporadic that if we treated the phone as the person, we're way overestimating sleep. So our approach, which accounts for this and tries to correct for this bias, this is what you end up getting. Much more realistic. So hopefully I'm painting a compelling case why you need kind of a robust modeling methods to turn this data into measures. In this case, we're getting time to bed and time to wake, which are much more trustworthy and probably more reliable. And we have validated them in a lot of cases where we do collect self-report, and also validated against wearable devices. So that kind of answers the question, what happens here is with our approach, with the unadjusted approach, we would way overestimate sleep, but our approach does a better job. This is kind of painting the same story. I'll skip that slide. We did show in practice that with, if basically is, I'll just, without describing the methods here, in our data, we estimated in our validation data, this is the amount of bias, overestimation of sleep duration in terms of hours that you getting with 4 competing methods. It doesn't matter which method you're using. If you treat the phone as the person, we were getting, you're overestimating sleep duration on a nightly basis by as little as 2.5 hours to as much as 4 hours. So we're way overestimating the amount of sleep you get. But with our approach, it goes down to a bias of only half hour at worst. This is the deviation with our approach. So, basically, this is showing the importance of really understanding that you cannot treat the phone as a perfect proxy for the person. Let's see. So I realize probably should wrap up in the next 5 minutes, and I did want to connect this back to clinical outcomes. So far, I've really focused on talking about some of the modeling approaches that we've used to take the raw data and turn it into meaningful measures of behavior. I focused on sleep and routine so far. I've also done a lot of work on measures of mobility and activity. But I just wanted to give you a little glimpse into some of the behaviors and some of the work we've done in this area. But let's take that nice, pretty, colorful data frame and connect it back to some clinical outcomes. So, for example, I mentioned that we have a routine measure. Well, we wanted to see, does that routine measure, here, if you look at this plot on the right, this is showing like hour of day phone use for 3 different people. We have a measure called the activity rhythm metric. It's like a diurnal rhythm quantification of the strength of a routine, of a diurnal routine. And these are 3 different people from our study. And this is someone who scored high on the metric. They have high variability over the course of the day. That means they have a stronger routine. Like they are definitely using their phone way less in these nighttime hours and using their phone more in the morning. Now over here, this is an example of someone with a low ARM. This is someone who, at least with respect to their phone use, there's very little routine. So we cannot just, what I mean by that is that you cannot look at the time on the clock. I cannot look and say it's 4 a.m. and I can't make a more educated guess about how you're using your phone at that moment than if it was like 2 p.m. Whereas for this person, they're probably regularly sleeping at the same time of day. This person is not. And they're not certainly using their phone at the same time of day. So we wanted to see, great, fine, we have this routine metric. Does it actually mean anything? Does it correlate with anything useful? So we looked at that. Now, it wasn't the biggest, we had, I think, in this study, if each point here is a person, I believe that we had about 42 people with sufficient data to look to see if there were any trends between our routine metric and this is self-reported mean sleep. So, we did see that people with stronger routines slept longer, and that was statistically significant. There were some sex effects. There was some borderline, like self-report of mood, but really the power of the study was fairly weak because there was only 40 people involved. But there's probably a signal here. So we connected, this routine metric is related with a lot of demographic and some clinically relevant behaviors. We published this in JMIR Formative Research last year. I wanted to give another example. I know I'm rushing a little bit, but I did want to cover this one. This is another example of change point detection. I think this is one of the most exciting examples. I talked a little bit about suicidal ideation at the start, and I feel like smartphone digital phenotyping is perhaps one of the best bets we have if we really want to tackle using it for the purposes of just-in-time adaptive interventions for intervening for suicide prevention. This was one example. Sorry, I'm talking about suicide. This is actually an example from where we wanted to see if smartphone data alone, passive data alone, could be used. So all those features that we get just passively, we're not asking you anything. Could we have anticipated? In this case, it was relapse from schizophrenia. So this was kind of a use case. To me, I would love to apply this in a cohort of a larger cohort where we are tracking people who are at high risk for suicide. If anyone on this call could point me in the direction of someone who would be interested in doing that. And I know there's like Army STARS study. There are some studies that have collected smartphone data. I haven't been a part of them, but this is something that is personally of interest to me. But in terms of the methodology for this, it would be very similar to what we've done here, which is we had relapse and, in fact, objective assessments of relapse, because these are, the red line here is, for example, a date of hospitalization for a particular patient with schizophrenia. And I'm just showing you 3 of the features. As I've talked about, we collect many more than just these 3, but we do multivariate change point detection on these features. And we wanted to see, just using smartphone data, nothing after the date of hospitalization, just prior, could we have detected a significant change in behavior that would have tipped us off to this relapse event? And so, we have this over a sample, but I'm just using one participant as an illustrative example of why multivariate change point detection is really important. Because sure, you can measure how many minutes someone is spending at home. That alone is probably not going to be enough to tip you off that relapse is coming. And in fact, yes, we got a change point, but really, what, like they're they're spending an hour less at home for the previous week prior to relapse. That alone, like that happens all the time. But when you culminate all of these changes across all these features, I'm just showing 3 here, but again, we applied this to 35 features that covered social behaviors. These are some mobility behaviors, sleep behaviors. If you look at all of them at the same time, and if you notice a small change across all of them, simultaneously all of them changing is very unlikely. And that is what enables us to get a statistically significant change in behavior. One alone is not enough, but the culmination of their signals stacked on top of one another, we could have, in fact, in this case, detected that there was a change in behavior and perhaps flagged them for an intervention in time. There's, well, this test statistic shouldn't mean anything to anyone on this call, but basically we had a really significant change point in this particular person. We ran this on a whole sample. We did find a higher rate of change points in the week prior to hospitalization compared to other times, times during follow-up that did not precede hospitalization. And actually, I'm going to skip this last one because we're a little over time. But we do have like a sample size calculator. If you're interested in this, we also wrote a paper on, what kind of statistical methods you can use in digital phenotyping studies, what's maybe appropriate, what's not. We have a sample size calculator where, when you're designing digital phenotyping studies, you have to not just consider your sample size, but also how long do you want to, what's the length of follow-up that you desire? And those are kind of 2 variables that matter a lot with respect to power, both for association studies as well as for like N of 1 models, like the change point detection I showed. So I would point you to that paper if you want to kind of learn a bit more about how you might go about designing a digital phenotyping study for yourself. I want to thank, this work was largely supported by the NIMH, and also I showed a lot of work done done by my PhD student who recently graduated, Benny Wren, Francesca Mendel, who recently graduated, is at the FDA now. So I want to credit them with a lot of the figures and slides you saw today. I'll stop there.
Thank you very much. Sorry, this is Leah Rubin. I was on another call like prior to, and so thank you to Barb for introducing you. And of course, my camera's not working, but that was an absolutely fabulous talk. This is very relevant to, I know you've kind of been focused on depression, but very relevant to HIV and a lot of the kind of RDoC factors that we're interested in as you think about sleep and wake. I'll go to the chat first to address some of the questions and then kind of open it up. Rob, Paul, I know you joined. You want to unmute and ask your question?
Yes, thank you, Leah. Again, great talk. Really enjoyed it. I have a question about the data that you just presented regarding the prediction of the hospitalization. And curious about how the validation steps were done and what the final metric of performance was. Was it F1 or AUC or just, and what's the accuracy of that of the final model?
Oh yeah, well yeah. So if we were indeed building a model where the outcome was hospitalization, then we could have prediction error. We could have AUC. We still can have that kind of sensitivity analysis because for change point detection itself, we have a significance level alpha, which is often dictated by, if you have a lower threshold for significance, that means it's less likely to flag a change point in behavior. I will say that those change point models, though, are unsupervised in that hospitalization was like we're just purely looking at change points in behavior. So we have these multivariate feature vectors, and we are looking to see if there's a change in behavior. This is completely like when we're doing this change point detection, we're not looking at hospitalization. So we're not actually predicting hospitalization. What we do is that after we've looked at the course of follow-up and identified locations of change point, we like overlay their hospitalization on top of that to see if there's an alignment, see if they proceed. So, some I'll go back. Yeah, so that was in response to another comment. So with respect to, we did do sensitivity analysis, which is with respect to both the window pre-hospitalization that we used to see if basically what we looked at is the rate of change points in the week prior to hospitalization. And then, so suppose you follow someone for 3 months. What if they were hospitalized twice? Then we have 3 months of data, and we look at, say, the week prior to each hospitalization event, and we put that in one bin, and all the other days we put in another bin. And then we look at the rate of change points in those two bins. And we found like a 70% higher rate of change points in the bins of days prior to hospitalization. Now, we did not just do 1 week. We said, like, what if we looked 2 weeks prior? What if we looked 5 days prior? And so each of these, we wanted to see how, like, it might change what our final number is, but it was fairly robust. There was clearly an increased rate of change points. But we can't do something like an AUC because we're not fitting a model where the outcome is hospitalization, right? We're doing a completely unsupervised multivariate change point detection and then just overlaying hospitalization afterwards. So we had to do a metric like this. And actually a benefit of this is because hospitalization was not used in our model, we're not concerned with, normally you need to separate training and validation and testing when you're doing prediction because you of course need to do out of sample performance. But in our case, our change points were, we didn't use hospitalization info at all. So by design, there's a disconnection between the output we're comparing it to and our change point detection model. So, we could just treat our whole sample at once because it was unsupervised. I don't know if that answers.
Yeah, no, it does. I appreciate the response. I guess you could look at a comparison group that wasn't hospitalized within a time period or a similar time period to see if those features still load into a traditional prediction model. But
Actually, we
totally
did, because not everyone was hospitalized in our study either.
Right.
So I gave the example of we followed someone for 3 months and they were hospitalized twice. That's quite rare, actually. I think the number we had maybe like 12 people, 12 total hospitalizations. So it across a sample of less than 50. I don't remember the exact number. But when we actually compared these rates of change points in the days prior to hospitalization, there were people that were essentially controls and that they only contributed to the bin of all of their days essentially corresponded to no hospitalization days. They didn't precede hospitalization. So there were kind of controls built into it. In fact, there's way more of those control days, obviously, as opposed to the pre-hospitalization days, just because of the rarity of that event.
Thank you.
Yeah.
He's our resident machine learning expert in the HIV arena. As we were talking all about machine learning prior to your call. But it's just really fascinating to see how you're using wearables and phones, just within depression. I mean, this is something I know I've thought about, and I think there are some folks at UCSD as well who, is it Rhiannon Moore? I thought she's doing some EMA work or was doing EMA work.
That's correct. And also Brooke Henry with our group, especially exercise, physical activity.
Oh, is this with wearable devices or a smartphone?
Oh, I think probably both, depending on the
Okay.
specific application. Yeah. And I don't think they know about this or are on the call. So I'm going to send them an email and just direct them. Barb, you said the meeting's being recorded, so they can take advantage of your expertise, because I agree it's a really nice way to integrate very high density data. Yeah,
when I think of the domain of mHealth, I do think of it on a spectrum a little bit, where on one end you have wearable devices where the data is generally going to be much more reliable. If you just think about, like, also it's fixed to the person. so there's a lot of reasons why it's more reliable, but so I would say it's like more reliable, but it's harder to collect over a longer period of time, and it's also not as scalable, right? Like you have to give everyone a wearable device. On the other end of the spectrum is the smartphone, where the data, there's a lot more problems with the data, as I talked about today. Like this sparsity in the data is a huge problem. Some of it can be solved with robust statistical models, but you're always going to have like worse data quality on the smartphone side. I mean, these are one thing that I always advocate to all my collaborators is that don't use study provided phones. You're completely like you. And fortunately, we see like a similar penetrance of smartphone ownership across demographics. So with respect to fairness, there's less of a concern there. But like having smartphone ownership as a inclusion criteria is pretty critical, because if you're providing people phones, the whole point of this is that you want people to be intrinsically motivated to use these phones, or else they're just not going to use them. If you're giving someone a phone that they didn't already have, and you are expecting to get good quality data out of that, you're going to be you're going to be disappointed, especially in a longer term study. And so it's both not feasible to hand out, especially if you want a big cohort. With smartphone data, you can do that. People own phones. This is free to collect, essentially, right? Like this is data that is their phones are collecting on a daily basis constantly throughout use anyway, that are currently not being used. We're just saying, of course, being really transparent with exactly what we're collecting and exactly who's looking at it, so we get good consent from the participants who are involved. But we're basically just saying, can we use that data, which is being collected anyway, and use it to treat you better. And so like from that perspective, I feel like there's very little to lose. If you're designing a study, like why not ask if someone wants to add this app to their phone? Again, our focus is we really don't, it's super important that we're not adversely affecting battery. This really should have no change to how they were living their life before. And then the side perk that a lot of my psychiatrist collaborators like a lot is the self-report aspect. You don't have to use that if you don't want. If you really like how you already do self-report, you could just do the passive data. I love the passive data. That's, for me, the passive data is way more fun. But there is an appeal to be able to send out EMA to a phone at any time of day that you want. And so a lot of people do take advantage of that as well. But I'm an advocate here. Of course, I'm advertising the use. If you haven't heard or thought about using smartphone data before, I certainly, I want to increase the visibility of it.
And I think some things that at least we've come across with, we've worked, and Howard Fox as well, with Joan Severson, who developed Brace, more of a way to capture more of the, not so much passive, although you could get to passive, more active data collection. And then part of that became, wait a second, they don't have iPhones, at least the participants or, populations that we see. And so whether there are certain, or a lot of our folks have burner phones and then they toss them. So
right.
So we have a very difficult group to phenotype, and they don't always have the tech that we want.
Yeah, I mean, in an ideal world, I do always advocate for having that as an inclusion criteria. I will say I'm part of the data coordinating center at Penn, which is the DCC for a big UL1 called Rural. I don't know if anyone on the call knows about it, but they're focused on basically doing deep phenotyping in the poorest counties, and I think they actually like pick the poorest counties in the country. And we've actually done most of the data collection at this point, but like sending out mobile vans to provide treatment and do a lot of these like deep phenotyping assessments. In that case, we did have to, basically there was an option of, and it was a very interesting discussion actually in the planning of that study. We had to be able to provide phones to these, they were specifically selected as the poorest population in like the deep South of the country. And so in this case, we definitely could not require that as an inclusion criteria. But then there's like the fairness issue of like, okay, what if someone already has a phone? You're giving phones to some and not to others. So I don't remember exactly what we settled on, but like there was a monetary perk given to people who didn't want the phone. And but anyway, they, you know, in some cases, I would say that you can't make that part of your inclusion criteria. But and in this study, you know, as someone who works with the passive data, I just have to, you know, bite the bullet and do the best I can with the data that is provided on study provided phones. It is just undoubtedly worse quality data though. And
Yeah.
if you're giving someone a phone for the purpose of the study, they're not going to use it long term in the same way that someone who already owned a phone would.
Thank you. Any other last minute questions as we come up to the end of the hour?
Yeah, Ian, this is Barb. I have a question. First of all, I really enjoyed your talk. Fascinating. This is totally not my area of expertise, so my question perhaps is a bit naive, but I was just interested in how the passive data that you collect correlates to the self-report data. So if you ask somebody how they sleep and they tell you the quality of sleep, how does that actually correlate to the sleep data that you collect passively?
Yeah. So for that one, this was this table here. This was based off of a validation. What basically we looked at a portion. This is from a study where we had a week of an actigraphy watch in addition to the smartphone, and so we used the actigraphy watch as kind of like the gold standard, and this is representing in hours like the deviation in the smartphone-based estimate from that. So this, when I'm saying that like using smartphone data alone, we're about half an hour off of the true sleep duration. This is compared to, how do we know the sleep duration? From the wearable device, from the actigraphy watch. I will also add what I didn't cover, and we have a biometrics publication on this neural network approach we do, where we are actually predicting depression and anxiety. We have an approach that in a longitudinal context does that prediction. And these are mean squared errors. This is this is absolute. Anyway, basically, we do a really good job of predicting. In this case, this is self-reported depression and anxiety purely using passive data. Like if we just observed those 35 features representing sleep and mobility and activity, etc., we built a predictive model where we said, what would your self-reported depression be? And we did a pretty good job of that. And so again, the goal of that is, and maybe you can train the model with a little bit of self-report data, but it might not be. So if we ask you to do self-report on depression and anxiety for 2 weeks and use that, we have a population-based model, but also learn about your own relationship between our passive features and the self-reported outcomes. Could we then 3 months from now, where we didn't have the luxury of doing self-report, but we do have the passive data, could we make an educated guess about what your depression and anxiety was using this model? That was the focus of this. So this is more directly, and again, I don't have time to talk about this study, but this is more directly modeling this is a more classic prediction problem, right? Where here we did have to do validation and testing because the outcome was baked into our model itself. But anyway, if you're interested, you can see this publication, Biometrics, came out last year.
Excellent. Thanks. Thank you.
All right, so are we at the hour?
We are at the hour. So anyway, thank you again for an awesome presentation. Really enjoyed that.
And again, anyone on the call who is interested about learning more or knows someone who might be interested in doing more, I really want to spread. I feel like smartphones should be used as a tool of data collection because there's really no loss to, even if you're just using it for passive data, it's no additional burden. It's really easy to do. If this is something that's interesting to you, reach out to me. I'd love to talk.
All right. Thank you.
Great. Thanks, everybody.